Okay. Okay, so the topic is linear functions, meaning, I mean, the whole course is about linear functions. So what's so special about this one? This is really, we're still doing a review, but the laptops and the cell phones. So these are just the functions of one numerical functions. Numerical functions meaning input and output are just numbers, and so this is the simplest setting for our linear. Okay, so we're reviewing things that are go way back. Okay, so the simplest linear function is a constant function. We're not looking at the constant function at one as a single one anymore. Anything is we're looking at classes of functions. So these are what all the constant functions taken together look like. Okay. Then always think in terms of every function is looked at, no matter what dimensions are, as a procedure, as in all the angles that we can think of, we were looking at them. So it means graphical representation, the algorithmic representation, numerical representation of table, and just the well, that is for now. Okay, so then we moved on to functions beyond constant. Okay, so it's a classification, if you like, constant function, then linear. What's next? Quadratic, yes. And good news. So that's what we will be doing, right? So the constant function, in fact, constant functions are so boring that we're not gonna be worrying about it. But it is, if you remember calculus, that's where calculus starts, is when we move beyond linear. Okay, so linear functions then are classified based on their slope. Okay, so the slope is just once again rise of the run. Goes way back. But we're taking a slightly different angle on this, and for multiple reasons. One is that higher dimensions. So is the meaning of the slope? Remember, we started with the problem of mixtures. Okay, and so remember that it's this slope of the line. Okay, so of the line, and we know that there were no there were lines. Okay, but we know that if we go to high dimensions from those mixtures, and then we have more than two, then instead of lines, remember we have planes, right? Plane space are the lines on the plane who have little planes in space. So which means that this is not going to hold for long enough for us to just one number characterizes the whole linear function. So in high dimensions, then what's the meaning of the slope of a plane? What's the meaning of the slope of a plane? Extrapolate from this. How would you can tell the sloped plane or non-sloped plane? What's a non-sloped plane?
Line parallel to the x-axis.
Well, yeah, that's a line. What about a plane? So from that idea, go to higher dimensions. So always try to explore what's going to be happening in higher dimensions. We're doing a review of familiar business in dimension 1 and 1, and then in high dimensions, like I said, there will be planes in space, like this, literally. Okay, so slope. This is slope 2, and that's slope. All of these are sloped. So this one is not sloped, right? So once again, a constant function, and the slope is 0. You would say you want to have a number. So slope is a word, right? On one hand. On the other hand, it is actually once you get to mathematics, then it's a number. Okay, so in one number characterizes all lines. Okay, so that's what we saw last time. This is how it's computed. This is once again the computation. They can be computed in a that doesn't matter how it's computed and where it's computed, it's coming up next. But the problem here is that can you characterize a plane with one single number of sloping? Why not?
Because you would have to look at multiple dimensions since it's not.
Multiple directions, right?
Yeah, right.
Multiple directions. So you can have one slope in this direction and different slope in that direction. You have, in fact, infinitely many directions. So we know it's still, the slope is still valuable, right? So we still, once you choose a direction on the plane, you are walking down the straight line, which means that you are right in this position. So you can speak of the slope the same way, except unfortunately there are infinitely many directions, so we don't know which one to pick for now, but we will. Okay. So yeah, so infinitely many directions. And they are, each of which will have a slope.
Not sure what.
What?
You like, we're working within the plan, the plane. What difference would the plane being sloped make? You know, like if it's tilted, but we're still working on it, like on a two-dimensional space, even
Okay.
if the plane is
Well,
tilted.
what it creates is elevation, right? Elevation changes, that's the slope. So if it's terrain, it happens to be flat, flat but not flat, so it's straight but not flat. So then as you walk, elevation changes, and that's just the same way to say that you were experiencing a slope, right? Literally, the word slope does not come from a road necessarily, but from a terrain. So a slope of a hill, right? So it literally is the change of the elevation as you walk around, and so there's a slope there. The idea of a slope as a word, but the slope as a number is then what the point here is not going to work anymore. Okay, so once again, you're reviewing this business. This is how it's computed. Any 2 points picked, so you can test yourself. Any 2 points on the straight line can be picked, and the computation of the slope works out exactly the same, producing the same slope, which is in contrast to quadratic. Okay, anything on the quadratic, anything non-linear will have literally what the meaning is that the slope is different locations. That's what you learn in calculus. So once again, we start speaking of the change rather than run of the run. So it's just too geometric anymore. So this is more about data than as in contrast to this one or that one. All right, so this is geometry. If we this one is geometry, right? And this is more like data. Okay, so meaning that it could be still geometry, but it could be quantities that just change change and maybe related to each other somehow, which will produce the slope. Okay, so once again, the computation is any 2 points. Not only that, you can change the directions as well from A to B or from B to A. It makes no difference whatsoever. The minus sign appears in the numerator, appears in the denominator. You end up with with cancellation. Okay, so why is the slope the same at different points? The picture is supposed to suggest why. Why is the slope same in different locations? Well, it is a straight line, but can you make a geometric case why it's the case? Why it's true? Why there's a rise run over there and over there, but the producer result is the same. So the idea is double, let's say double rise run, double rise. Okay, so that's the different rise and run will produce the same slope because they change proportional. Okay, so that's how we explain how we interpret that statement. But what is the geometric argument that to be made in favor if anybody recognizes the picture? Maybe one triangle, the other triangle. from Euclidean high school geometry? Remember anything like this? What's the how would you call these two triangles?
Would it be congruent?
No, they're different shape. So not congruent is exactly the same size. What is they look kind of the same, but not exactly. What's the word? Similar, right? Similar, so meaning that they have the same angles. Okay, so and then a lot of things you can demonstrate about them, and that is they proportional, meaning that if you increase one side, if you increase one of the dimension, all the dimension increase, and that's the similarity. So it's not squished or stretched with respect to each other. So that's the geometry. If you learn those things about the geometry about similar triangles, then you can prove indeed that if the sizes match, if the sizes are proportional, then the angles are the same, and vice versa. And there, that's we conclude that that the slopes are the same if we were to do it under these circumstances, because the angles are the same. That's another thing that we learned from geometry, is that parallel lines intersect at the same angle. So that our line is here. We cross it with two horizontal lines, two vertical lines, and all the angles are the same. That's once again we are taking it from Euclidean geometry that we learned, and then we apply it to what we call this thing that once we start speaking of numbers rather than just a crossing of lines and circles, it's called analytic geometry. So this is just Euclidean geometry. They did not have the analytic geometry because they did not have the Cartesian system. Okay, so they had to wait until Descartes for like 2,000 years or so in order to get started with analytic geometry. But behind it, still Euclidean geometry. Why analytic geometry works? Because Euclidean geometry works. Okay, so that's the case here that you can make why the angles are the same, and the rise of the run as is once again gives you the same number. You can reinterpret it in terms of trigonometry. What's the meaning of the what is the meaning of the slope trigonometrically speaking? We have a right triangle. What is it? Right triangle. Rise of the run, but also what? We take this one over this one. What's called? You know what? In a right triangle? No, this is the hypotenuse. Okay, this is say A, this is B. What's the meaning of A over B? Trade word. In trigonometry, what do we call it? Hinge, right? So, so these are this is the line. Once again, you can once again, if you remember a bit from calculus, that's what the tangent or the slope will tell you. We're going up or down. That's the number positive we're going up, negative we're going down. Once again, so it matches up. This is once again, if we take all the linear functions and put them together, then we create this some kind of a circle of lines, and the slope are changing in the counterclockwise directions from negative, here it is, from negative infinity to positive infinity, with 0 in the middle. Okay, so these are all the linear functions are here. Okay, so you can imagine once again that's dimension 1. You can imagine how in dimension 2 it's not going to be as easy, because you can rotate it. You can think of a plane. Right? So there are several things that you can say if you fix location of the plane in space. You can do this, you can do that, and you can do this too. Okay, so so in other words, there are many more than one number. Let's say that you might worry about, and there are more degrees of freedom. Let's say. So how many degrees of freedom of a plane you have if you suppose the point is fixed here? So how many degrees of freedom? The number of degrees of freedom, which is what this is 1 degree of freedom for lines for the plane. Yes. 1 degree of freedom, and here 2 degrees of freedom. Which is, it's not entirely obvious. So you can't guess right away because there are infinitely many ways you can do it like this, okay? But it turns out that if you can split it into this and that, so you change it this way and then change it that way, and that's sufficient. You can get anything else. So so there are 2 degrees of freedom. Okay, so vertical lines are excluded, right? Vertical lines are excluded because the slope is, and one can use, why can't, the picture shows why it is not advisable to think of a vertical lines as slope equal to infinity. That's, you can see why we don't say that the slope of the vertical line is infinity. Look at the picture in the middle.
Both positive and negative.
Right, if you say infinity, and which infinity? Right, so it could be one, and we definitely look at it, we know that these are not the same infinity, right? So we go from you can have very negative, and that somewhere at the end of that road is negative infinity. You start rotating the opposite direction, then you end up somewhere with positive infinity. Two very different things. And so you can say it's kind of infinite, but infinite as an adjective, but you don't say it is infinity because we don't know which infinity it is. Okay, so the slopes have this drawback. This is point slope form. Okay, looks familiar, right? So mx plus b, m is computed in the manner we just discussed. So this is a linear. This is a big part that separates us from from experiencing linear algebra before. Is this, and the terminology is frequently might be confusing. Is that this is definitely a linear function? You've seen this many times. So where is and then there's a linear operator. So what we do is just drop b. So b is so unimportant that we don't care about to know about y-intercept. Our concern will be about slope, the slope or the slopes in high dimensions, and that where that line or plane is located is less important because we can always take care of it by shift. That's what, remember what b is. It's nothing but a shift, and that's why it is by far less important. Okay. So once again, I break the linear function into steps. Okay, so we'll multiply by m first, then add b. So that's the flow chart of the function. Slope intercept. Once again, this is the standard way of the best way to represent a function, I suppose. A linear function. The slope is there. Y-intercept is also visible, but that's not the only thing that we might encounter because well, there are alternatives. Remember, there are another ways to represent a function. This is slope intercept form, and the other one is well, if you don't remember, here's another way to look at it. It is you can represent a function with a straight edge if you have only 2 points. Where those 2 points would come from if you know the slope. And once again, we're concentrating on the slope. So if you have a slope, that's how it's computed. The second point is found. 1 step to the right, and then 2 steps up if the slope is 2. So literally 1 step to the right and m steps up or down, depending on whether m is positive or negative. And then you can just take a straight edge and draw that line. That's all there is. So even though once again Euclid says that you need 2 points in order to produce a line, and it's still true, except now we can get the second point from the slope, and therefore point slope form works. So this is a y-intercept slope form where that point is the y-intercept. So it's not just a special form of what we are after. So y-intercept is just the point on the y-axis. So that's it. But any point can be chosen, as you can see, no matter where we start. If we know the slope, we can find the second point, and we have the okay. In fact, we can go in this manner. 1 point at a time, you can draw more and more points, and it already looks like a straight line. If it's not convincing, make the step shorter, and these points will be so close to each other that you will definitely have a straight line. Okay. So we can go from left to right or right to left. That's the crucial part about if we are about trying to find algebra. And if we think of functions of a linear function as exactly that, there is a slope, and then a number that is given, and then there is always a point that's given to us. So what's the equation? Let's do it from scratch. You can go with the one to the left or to the right, and then you know what the rise is from the slope, and then you can compute x. Okay, so that's one way to look at it. Or you literally think about points in just points on a straight line and just computing the slope from you have points, and then from the points you find the rise and run, and that's how you have the slope. So this is the definition of the slope. Once again, one thing to be learned is worthwhile is division. Division is overrated. Okay, so naturally the slope is one number divided by another. But remember, the division always comes from multiplication. So it's more about proportions than about actual division, and we'll have a few examples of that later to see how you don't really have to divide. So the problem is that you cannot divide by zero. So it seems like a very valid equation, right? So a rise with a run, okay, so there are 2 points at A and X, and then the coordinates are respectively X, Y, and X naught, Y naught. So then it is still rise with a run, but the run cannot be equal to 0. Okay, so that is not the equation of the line, right? It cannot be the equation of the line because X cannot be equal to X naught, so it is a line with a hole. Okay, so the only for a single reason because we choose to divide. So let's avoid division and let's instead just multiply it out. So this is what we do. It's the same. Look at these two equations. It's the same thing. Only I brought the denominator up into the other side, and so as you can see, there's no division. There's no problem, and so that point that was excluded is not anymore. And it's totally valid definition of the slope. It's a number. Okay, so you have given a point and any number. You form this equation, no division whatsoever, and that's all there is. Okay, so once again, there is no division. And no division, no division by zero, no trouble for us to worry about. It's not an equation, so once again, it is a relation. So that's the drawback. So y is not expressed explicitly, but only you just have to move y to the y naught to the right hand side, and then you have your function if you like. So you can think of this as the definition of the slope. So whatever that number is that fits, that gives you the slope. Once again, there is no division, and so there is certain advantage to it. So x over y. Once you have a relation, you can look at it as either one function or the other function. So as you can see, relation at the top, and then there are 2 ways to at least to attempt to produce a function. As I said, you can pull y naught to the right hand side, and then you have a function on the left, or you can rearrange everything and just go with the x. Okay, and so solve for x, which the form is exactly the same, but the slope, as you can see, is the reciprocal. Okay, so because you have to divide by m at some point, which means that in the original equation, m could be any number, and here m cannot be equal to 0. So it's one or the other. Sometimes you cannot have both. So vertical line or horizontal line. Horizontal line, you cannot, the E is excluded on the right. The vertical line is excluded on the left. So once again, no horizontal. And this is no vertical. Okay, so once the advantage of this form, look at the advantage of this form is once again, even though there's a relation, it seems extra work, but really you can see all the geometrical ideas are here. So the rise is visible, the slope is visible, and the run is visible. So what's in parentheses are rise and the run, and the coefficient between them is the slope. Okay, so it's proportion between so what makes a straight line is a rise is proportional to the run. That's what makes a line. Okay, and then if you care, you find what that proportionality coefficient is, and then you call it the slope. So that's another way how to reconstruct the whole thing. Okay. Okay, so once again, identify things. The point, how with the rise, the 2 points are chosen ahead of time, A and X. One of them is fixed, and the other one is variable, so that's x uppercase is a point xy, okay, and so we pick the coordinates from both of them and plug them into appropriate places. So rises for y's and runs for x's. Okay, so incremental motion, once again, you can go proportionally. If you don't even need m to be for example a fraction. So what if m is a fraction q over p? That's how you can now plot it. You make p steps to the right. Hold on. So the slope is 3/2. Okay, the slope is 3/2, which means that you can build the line by going 2 to the right, denominator the run, and 3 up the numerator. Okay. So that's the geometry. Let's take a look at a little bit of data as I promised, and that is the idea what the rise of the run is. It's a made up word. Okay, so in mathematically speaking, so we have the data on the left. Okay, so the data is literally we're walking on a staircase or terrain and then move forward by 3 miles and up 12 miles. We divide as a summary. So that's what has happened is on the left. And then we want to summarize our trip. And then what we do, we divide 12 by 3, the number is 4, and we call it the slope. This made up word. Okay, so you don't really need anything what's on the to add anything to what's on the left. You might want to summarize, and in some sense there might be insight. So you have 2 numbers on the left, you're replaced with 1 number on the right. So it is a summary, so you have less stuff to worry about. But as we know, you cannot replace 2 numbers with 1 and think that you didn't lose anything. You surely did. Okay, so that's once again the actual data, raw data. Is visible on the right, on the left, and then you summarize it on the left, producing the slope. Okay, so if you're willing to do division, if not, then you just keep it. And in many situations, you can think about probably, do I really have to? Do I want to divide and produce a summary? And well, there are more examples. We going on with when a situation is identical, mathematically speaking, but the data is different. So this is geometry. So geometry meaning that the horizontal and vertical are both distances. Okay. So here's another one. This is definitely from calculus. Now you're walking on the straight line, and then the horizontal axis is time now. Okay, so a totally different situation. Okay, so it's not about geometry anymore. And then the our summary is the speed. So we walked for 3 hours and then we covered horizontally 12 miles. We divide, we get 4, but what is 4? It is, we call it speed. So once again, the trip was on the left. The raw data is complete and doesn't really need anything. But if we want to some insight into what was happening, then we want to divide and produce the speed as the summary. Well, naturally, that's not it. So let's have more examples. Here's another one. Suppose we have a metal rod, and then it is 3 inches long and weighs 12 pounds. Okay, if we divide by 12 by 4, we end up with the density. We call it the linear density. Will be pounds per inch. Pounds per inch. Okay, so once again, 3 situations right there in front of you. Mathematics is exactly the same, but the interpretations are entirely different. And once again, the point is of producing the slope is producing the summary. Okay, more examples. Another example: trade. You bought 3 pounds of apples for $12. Okay, you divide 12 by 3, and that's the price per pound. Okay, so another one. Every time you see division, there might be some once again there's a slope there. You don't really call it the slope anymore because the slope is remember it's the tangent. It's actually unitless. Okay, but all of these are all unit. They have units. Speed have once again miles per hour. All of these have units. So it is meaningful difference between different items. So you can think of your own examples. So this is the math. Okay, so it's called the difference coefficient. Okay, change of x, change of y. You divide change of x by change of y, and you call it the difference coefficient. Once again, raw data on the left, and on the right, we just make up the word that best describes what is that we're looking at. So any examples you can think of? of the difference quotient appearing, and so these are 4 situations. I couldn't think of anything else. So, any thoughts of what else can be put on the list? 3 of something followed by 12 of something else. You divide, and then the answer is 4. And what is a kind of real life situation you can think of that would
Maybe like miles per gallon, so like you fill up your tank.
miles
you
per gallon? That's a
check
good
the
example.
distance, how far you can drive.
Per gallon. So once again, I wanted the same number. Gas, 3, hold on, per gallon. So 3 gallons. Okay, gallons, and you covered 12 miles. Okay, so once again, that's your trip, right? The trip is right here, and then that's a summary. What?
That'd be a very big car.
Oh, it's a tank. Okay. Summary is then 12 over 3 is 4, and that is mileage. Mileage, I guess that's the right word, probably. So yeah, you can think of in fact, so that's a good one, good example. It may be another one that's not as good would be anything that depends on time. So here I have number 2, your location depends on time, but any value could depend on time. So your temperature, prices depend on time, and once again, you can just divide it as a summary to produce some kind of a quantity. So in fact, so the velocity, speed of velocity is used normally in many what's describing phenomenon that have nothing to do with location, but a state. So state could be, once again, a temperature, blood pressure. You take a patient, and then it will have a bunch of vital numbers that are vitals that are each of which is a number, and they depend on time. And you're looking at how fast each of them is changing. Okay, so once again, you can call them speed or velocity of change. Okay, so once again, that's a good example of how linear algebra on the most elementary level appears, and what's the meaning of linear algebra is. It's kind of a summary of what's going on. Okay, so so a little bit about sequences, but not in the spirit of calculus, because we're not talking about limits. It's just a way of recording things in the form of a special kind of function, right? And so the idea of the ability to write in using so everybody familiar with the notation for sequences? Remember subscripts? Well, let's review this quickly. So the motion is not continuous, but rather incremental. Okay, so the difference quotient still applies, so you can speak of the speed if you want to. But the main thing is notation. Okay, so you put it on the list of locations, and assuming that time progressing one at a time of whatever unit you pick. Okay, so this is how the graph appears. This is how what you actually see on the, if you take pictures and kind of overlap, then that's what you see on the left. If you split it into video frames, that you have a picture on the left, as a matter of fact. And if you overlap, you have what's on the right. Okay, so that's the graphs of sequences when the curve itself does not necessarily merge. But once again, the point is a list of numbers that can go horizontal and vertical. So whatever you see in a spreadsheet or in many other places, it's a sequence. Okay, so the only thing that is mathematically needs to be added here, once again, 2 ways to visualize with dots or bars. It's Excel done it for you. Is this indices, and so that are the subscripts. Okay, so rather than having f of x, we have a sub n. So the inputs are, we call the index, and there goes as a subscript of the name of the sequence. So our sequence is A, and the like it's as if it is a location that we are recording them. We telling where we are. Okay, so within the sequence, the third element, the fourth element within the sequence, and so that's a big deal. And many computations are carried out in a manner that is repetitive. So it is incremental then, and so you do not do things that we're so used to in calculus. And it is you have the whole function in your hand. You have one formula. This is you might have to be forced, as we saw, one step at a time. So this is how you write it out. So once again, you take the list of numbers and just assign, you give each of them a name. So h sub 1, h sub 2, h sub 3. So those numbers that we have for the ball, they have different names, and so you can see different phenomena. Okay, so once again, A is the name of the sequence. Index is where within that sequence you are located. You can think of sequences as tags on objects that might be more complex than just numbers, but the most simple thing for us to deal with is the sequences of numbers. It's an address ultimately. So the A is the street address, street name, and N is the number. Okay, so once again, instruction, this is how we know this is still a function, nothing more than a function. You plug in the value into that opening, and then and on the left hand and the right. And so if I plug in 3, I'll have 1/3. Okay, so that's the words exactly the same. Graphing, okay, constant sequence. So let's quickly provide the main kinds of sequences. Power sequence made of power. So if we do have a sequence, increasing decreasing sequences, decreasing sequences, once again, so literally, as you can see, so what you learned before. So if the input, which in this case is n, if it goes up, what happens to the value of the output? And the answer could go up or down, in which case we speak of increasing or decreasing behavior of the sequence. Okay. So we care about that. Okay, so once again, the incremental nature of life frequently is not what you learn in calculus. Typically, more continuous motion. That's 90% of what you see in calculus is the continuous motion of objects through space, or maybe something like I said, temperature could be changing continuously too. That's totally understandable. But this is really what real life frequently is incremental, and so that's why sequences are so important. Right, so in this case, as you can see, so $20 you add every month, and then you sort of clearly that you can compute as far into the future as you like, but there is no at this moment an explicit formula for it. Okay, so that's they call it recursive. Okay, and then and that's frequently you do not are you looking for a formula or not? That's a secondary question. You should be able to define a function itself, the sequence itself, with the in this manner. So from a verbal description, as you have here in the very first sentence, here you're supposed to produce a formula, and then you plug in that formula into any kind of computer, including a spreadsheet, and you can compute as many as you like, a long table over there, and then you can plot it as well. So it's definitely increasing, and you also suddenly, once you plot it, you have right away inside that is actually a straight line. Okay, so that's generally what recursive sequence is. So the same formula applied again and again and again. So the output is or a recursive idea more than just recursive sequence is that some kind of procedure is repeated again and again, producing incremental sequence rather than one at a time, or rather than jumping into the next. So direct, you have a formula, and you know if you know nth term, so 100th term here, you can ignore all of this, and you can just compute a 100 by plugging into the formula. So n is equal to 1 n allows us to do that. If we, however, have what we just had, an plus 1 is equal to an plus 1, that's you cannot jump straight to 100th term without producing all the previous ones. So that's the idea. So arithmetic progression, remember that one. So adding constant number at a time. Okay. Once we move to compounded interest, that's not arithmetic progression, but once again you want to it is repetitive once again, in the sense that, I start with with a verbal description, and then you should be able to translate it into the language of mathematics, multiply by 0.01 every time to produce interest. You add it to the original, which amounts to, so what you get that $10 at the end of the year. Okay, so that's a sequence. You can compute it into the future. If you have a formula, the formula is uncomplicated. Fortunately, just nothing but multiplication by 1.01. That's extra. You have your principal. That's one. This is responsible for the principal, right? And principal or your capital. This is the interest. So instead of adding the same number, we multiply with the same number. That's what the exponential ultimately exponential behavior is. Called officially geometric progression. You can notice if you plot it once again, we do not have a formula, but we do see that acceleration and compound interest effect is in effect. You can see it right. So let's get visual. Called geometric progression, geometric growth, geometric decay, exponential geometric growth. Here, of course, it's a compound interest. One example, another one population decay as well. All of this covered by this little model. So I assume you've seen this before, just not at length. So we'll use it as needed, but really just a refresher. Okay, exponential decay. There are a bunch of examples, but ultimately it is just another example of a function that you're going to be using as needed. Okay, so let's skip that. So one thing is worthwhile whatever you're studying is producing sequences in the spirit of calculus, and that's just like in calculus you have a function and then you transform it to another function. Okay, so you can do this in sequences, and that's taking the summation is one of those examples. Summation of a sequence. You have a sequence 2, 4, 7, 1, -1, and then you can start adding them up one at a time. Does it sound familiar from calculus? Well, the sequence represents the velocity. What are we trying to compute here? What do we usually compute in calculus? If you know the velocity, what do you compute? So suppose time is 1 hour at a time. So I was moving 2 miles per hour, then I'm at the location of 2. Then I'm moving 4 miles an hour, I added 4, and I'm at location of 6. Then it is 7, I'm at location 13. Okay, so in other words, we are computing locations from velocities, which is what calculus does anyway. Does it sound familiar at all? Well, we're not doing calculus, but if any kind of link we can make to something familiar that is beneficial for you, so not. We don't want to disconnect this course from the rest of the mathematics. So it's just rearranging blocks. It's called the sequence of sums. Okay, and something that is also in calculus, and we need is the sigma notation. The sigma notation from calculus. So once again, if you haven't seen this, this is the time to see it. It's important throughout the course. And once again, the notation that we frequently see in calculus is the kind of this, and it's left hang there a while without explaining what it is, as if it is the difference is you imagine that it's computed instantaneously, and you have the whole thing in your hand, which we know is not the case. We're computing it. Look at it. We're computing a recursion. Okay, so a sequence is you start with say 0, and then you start adding on top of it one at a time. You don't know where you're going to end. Okay, so there is no formula for the where you are after n steps. Okay, so that's what this is. And if you are into computing, you can certainly, write something, you can write a short piece of code, right? So, or pseudocode, so based on this picture, or based on this. Okay, so anybody want to suggest how we write it? A piece of pseudocode, anyone into computing? What?
For loop.
For loop, okay, for, say, what is it, and let's say from 1 to, and to, I don't know, and uppercase. Okay, so that's the for loop. Okay, and what's missing?
Should initialize like a sum.
Okay, so let's call it sum. Okay, and let it set it at 0. Okay, then we go through the loop. And so sum is updated, right? Or whatever if you prefer. Let's just write the formula that is we already have. Sum plus whatever something is taken from that array of or string of numbers. So let's say A and. That's it, right? That's it. That's how you sum up the string of numbers. Just go one at a time, add on top of it. That's all. That's all. So that's the challenge, to forget about it if you study calculus without understanding what that sigma notation is. That's what summation is. Then the sigma notation is very confusing. Okay, so that's the sigma notation. It's S stands for sum, sigma stands for sum too. Once again, if you want to break it apart, that's what it is. It's once again, it's nothing but an abbreviation. Okay, so this is the beginning and the end is right there, either algebraically on the left or a pseudocode on the right. Doesn't matter. It's the same thing, and the sigma notation is hiding that complexity and recursive computation from the site, and so as if the whole thing has been computed. Okay, so and that's what we have here. Okay, so the once again identifying the top, the bottom of the numbers that you have to run through, and then at the end should be a number. Okay, so a sequence is given, and it's processed as a whole. You can do it one at a time, as I just showed you a minute ago, or you can compute the whole thing, and then in the end is a number. Okay. Okay, so you can go back and forth, so sigma notation is expanded, so you can just write all the numbers and then enter together, so. Just what it is, let me skip this, so exercise, if you haven't comfortable with a sigma notation, then a little bit of a couple of exercises would be probably helpful. Did I miss okay, I'm gonna be, okay, we still have findings. Okay, so sigma notation, okay. Oh, yeah, okay. Give me a minute. I just got to insert. Okay, so that ends the most basic review of the linear algebra and functions and pre-calculus that we're gonna need. So there will be a bit more here and there. You know, once again, algebraic geometry, a little bit of Craig, you know, once again to primarily for the slope. Okay. And what else? And then we're gonna add for things such as vector. Okay, so that's the main topic. Right now, we're just waiting for this to be inserted. So, any questions while we're waiting? of this stuff. Something helpful. For now, helpful advice here. Waiting. So read the syllabus. If you don't like surprises. Happen here. Yes. One more. Okay, so this one is here somewhere. It's still processing. So so I inserted the whole thing, but I don't have anything. So OneNote is no functioning here. Let me just open it with just so this one not opened. Okay, so Edge. Okay. Okay, so okay, so set 2 of lectures. So and so a little bit more advanced, but still review of certain things, and you can see some of the things that are familiar, and we'll go over them pretty quickly. So the image also known as the range. Okay, so once so there is really nothing tricky about it if you know what the range is. It is literally the very descriptive word of what we're looking at, the range of values. So it's not only the values that could be taken, but rather the values that are taken. So these are the outputs, and all possible outputs collected together produce a set. Okay, and so that set is called the range, or in a more in a linear algebra context, they're called the image. Okay, so once again, we go back to our function of boys and balls. Okay, so once again, the codomain is all the outputs, but the range is only the outputs that have been hit. So as you can see, the baseball is missing for that reason. So because nobody wants to out of these 5 wants to play baseball, so the only these 3 is the image, also known as the range. Okay, so basketball, tennis, and football, like this. So a function takes the domain and somehow moved it into the codomain, but it doesn't cover the whole codomain. Okay, necessarily, and which means that whatever is missing is ignored. And if we were to speak of image or the range, then the ones in the that have been covered and that the targets that haven't hit is what constitutes the range. Okay, so among the numerical functions, so let's so the word range is I presume is very much familiar. So let's just review things, especially with a few pictures. So if the slope of the line is not 0, as you can see, what is the range? What's the range based on the picture? So I'm taking the blue line. So on the right, I have 3 lines. and I'm taking the blue one, and I'm looking specifically at the range. What's the range? So remember the meaning of the graph. It allows you to actually get from each x to each y, and those what those arrows are supposed to represent. I'm taking, for example, 5 over here. Where does 5 go? It goes towards the line and then horizontally towards the y-axis. So input of 5 will produce -1 as the output. So all of these, what these arrows supposed to represent. On the other hand, you can another way to look at it is that the graph exists already, and therefore we can find the domain and the range by going horizontally, vertically. So the arrows that go horizontally go towards the y-axis, that's the range, and the ones that go vertically towards the x-axis, that's the domain. So what's the domain of a linear function? So you ask yourself what numbers are covered, because there are infinitely many values, there cannot possibly be infinitely many errors. So you have to extrapolate. You can see that they were not missing any values. Look at it, we're not missing any values on the x-axis. So every value in the y-axis is listed with the one that we concentrate on is covered. So if you see between 5 and 6, is it missing that value in the middle between 5 and 6? The answer is no, because we can still find a point on the graph that will hit that value. Okay, so 5.5, for example. But that's to begin with. But then the same story happens on the y-axis, it turns out. So the domain is, even if we don't have a formula, okay, so we certainly, if you know the formula, look at the formula, there's no division or anything like that, so you know the domain will be everything. All real numbers. With the range, it's less obvious, but nonetheless, it works out exactly the same way. And the graph suggests that it is y because as you go horizontally towards the y-axis from our line, you will get everything. Okay, so you can imagine that this line is smashed into the y-axis, and every target on the y-axis will be hit. Okay, so the domain is just as the domain is everything, so is the range. But so that's geometry. That's just visualization. But you can figure out the same thing about the with algebra. Okay, so look at the problem. Here's actually the algebraic problem that we're facing when we start speaking of the image, and that is every y an output. Okay, so is every y equal to, so mx plus b are given. We have that straight line, and we ask ourselves, is every y of x plus b for some x? That's the question is on the left. Okay, the question is on the left, and the right. The answer is on the right. Okay, so we asking what is that x? For given y, can we find an x? And the answer is yes, we can, as long as m is not equal to 0. Constant function certainly is excluded, and so the answer is always yes. So m is not equal to 0, so for each y, we can find an x. Okay, so that's what we're saying here, and that's the theorem that says exactly that in a more compact way. So the image is everything. So with the exception of a constant function, a linear function will produce as its image all real numbers. Okay, and that's a problem that you might encounter in calculus, and we were going to get to that. So what's the two equations that we're looking at here? So what do we describe? How do we describe them? The relation between the two. Y in terms of x in terms of y. What do we call it? Y in terms of x, and then we turn it around, and we got x in terms of y. Inverse, right? These are the inverse. So once again, because everything is linear, the situation is really simple, but all the business that you see in calculus, inverses are all over the place. Exponential function, logarithm, sine, arcsine, all of them come in pairs because why? Because well, we see why, and we solve the equations. Okay, range of x squared. So the problem is not very simple to be solved as easily in linear functions. So just an example, look at it, try to prove that you'll notice that x squared does not produce as the range all numbers, because it only produces everything above 0 and above, so that's out. So it doesn't produce everything, but once again, it makes sense to compute the other range. And x cubed does cover everything, and the graph suggests y. And once again, you can what literally has happened here. You take the graph of x squared, you take the graph of x cubed. What do you do with it? You thicken it. So I did it with Excel, and then narrow it down. Then there is nothing but the y-axis pretty much. Okay, so once again, the graph, that parabola on the left has been thickened and narrowed. So then it doesn't look like a curve anymore, but you can see what it traces on the y-axis, and it's 0 and everything above. But on the other hand, x cubed under the same transformation does cover the whole y-axis. Okay, so that's how you know what the range is. Okay, so it's another way to see it. You can say it's a projection. You can say it's a shadow. Imagine that the sun is to the right and it casts shadow of the graph on the y-axis. So that will produce the range. Yeah, that's what's the idea. You might remember certain issues here in the from calculus. So we're asking ourselves, can we find, we're given a C among the outputs, do we get it or do we not get it through the, can we get back? Can we get back and find an X that produces this thing? And then sometimes you hit, sometimes you miss. If you hit, then you know that C is in the range. If not, then it's not. Domain to domain. So if you want to know where the graph lies, knowing the range in domain will produce a rectangle. Okay, so the graph will be aligned here somewhere in that blue region. So so you pre-image or inverse image, inverse. So that's another word that pre-image. Oops, or inverse. I don't think I'm on this one. Pre-image or inverse image is for every element, for every output, we'll try to find all possible inputs that have produced it. Okay, so basketball is hit by these two boys, like to play Ben and Tom, and so the pre-image of the basketball is Ben and Tom. The pre-image of tennis is Ned. Okay, there is no pre-image. The pre-image of, how do we say it? The pre-image of baseball is, what's the word? What? Empty, right? Empty. That's right. Is empty, and the pre-image of football is that. So that's what it's called. It is what we saw not long time ago. It's about solving an equation. Okay, so each of these is like an equation. Each of the possible outputs could be serving as the output of an equation, and you ask yourself, where does it come from? And the pre-image will give you that value. So there could be two answers, one answer, or no. Okay, so so that's the range. May make sense. So once again, this is how we can find the pre-image of every point. It is you go horizontally, you cross as many times as necessary, and then as it happens, and then find the go horizontally. We're going backwards. Pre-image, inverse image. So we're going backwards from the y's to the x-axis, and so each of which will produce a set on the x-axis. And the answer, the size of that set might vary from one to the next. So the pre-image is here is 1, and then you have 3, and then you have infinite many. If you have a horizontal piece of the graph, then the pre-image will produce will be the whole equal as well. Okay. Okay, so transformation, that's a big topic, very important for linear algebra. Once we go to high dimensions, then in addition to all the interpretations that we have had of functions or visualizations, there is one more. So remember, so once again, we look at every function as a algebraic formula. What else? There's a graph. There is a flow chart. You can collect a bunch of data in a column, 2 columns of numbers. All of these are good. And then there is one more interpretation, very looking for something tangible. And then it is thinking on the function transformation. So in higher dimensions, why those ways do not apply anymore because try to think about transformation of R2 to R. So in other words, the input is the plane and output is the real numbers. So the graph would be already three-dimensional. We know that will produce a surface, which is not that easy to analyze the graph. The data also, remember, it will be a table of numbers. Okay, so which once again, any kind of detecting any kind of a pattern there is pretty hard. And then if you go to beyond it, is also number one is hard. If you go beyond it and you have from R2 to R2, and that's not a big deal. We already saw examples of that. We cannot. The graph lies in the four-dimensional space, and we cannot really see it's not helpful at all. So graphs, some of the things fall to the side. But if a transformation, then we can still do something with that one. R2 to R2, it is a piece of paper transformed to another piece of paper. Okay, so that's what we will do quite a bit of that. And then hopefully that will be serve as an analog for the high and high dimensions. But we start with dimension one. Okay, dimension one, that's where the transformation is. The x-axis might be, we know where each x goes. What is x-axis made of? Well, certainly not made of steel because, as you can see, there is some stretching there. Okay, so that's what we need to quickly detect. And so we think about, so this is a shift, for example. As you can see, each ax has been shifted to the same amount from left to right. The amount is free. Okay, so that's one transformation. The simplest transformation. You can think of it as if there is some drawing on, or rather, x-axis is drawn on a pencil. That pencil is shifted and matched against another one, and so that's what we think of them as shifts. You can do so. That's a shift. Okay, so you can the algebra is here. X goes to x plus s. That's your algebra, and the formula itself is literally you can live it like this. Remember, we can describe functions by formula. Don't have to have an equal sign. It's literally x goes to x plus s. But if you want to, that's how you write it. Y is equal to x plus s, and that's your function. Literally a very simple function. But we're not going beyond geometry anyway. Beyond linear algebra, so we're not worried about more complicated transformations. This is a flip. Okay, do you see how this is a flip? Right, so you see where say one goes to the other side, but so does two. So everything was to the left and to the right, and so that's what happened. Another way to see this is like a mirror image. Okay, so literally, so positive becomes negative, negative becomes positive, and even though it's not a very productive way to look at, you can just think about a flip. It's easier, but in high dimensions, a mirror image will be very. Okay, so once again, the flip literally it points in the opposite direction, and the algebra it matches. Okay, so x becomes negative x. So that's the flip. Not only you can see the language of how a language of algebra matches the algebra of transformation. Transformation is a flip, but also we flip the sign, right? So flip the sign, flip the x-axis. So that this is a fold. Okay, so a piece of wire, we fold it in half. They take the x-axis made of a piece of wire, we fold it in half and place it on top of y-axis. That's the transformation. You can see where numbers go. A formula you can think of. Can you think of a formula? On the right, if you look at the absolute value, right? Absolute value of x will produce the fold. Okay. It is actually not a linear transformation, so we will stay away from it. A strategy is a linear transformation. So this time it's made of a rubber string with knots indicating the markings where we are. Okay, so and then literally we can stretch it by 2, transform it and see where they land. We can shrink them as well, and that's very easy way to interpret it without, once again, there is no graph, right? So I want you to see that this is an entirely different way of looking at numerical functions, but other than the plotting the graph, visual but not the graph. Okay, and you can see how you can go to high dimensions instead of having x and y being two strings. You have a rubber sheet rather than rubber band. Okay, so you can do all kinds of stuff with it in high dimensions. Okay, so, well, expanding universe, if you want to think about it, so, yeah, so why we cannot see it, but it might still be there, distances increase. Okay, so shrinking, stretching, multiplication by a number, that's what stretching, shrinking is. You've seen this before, just to refresh your memory maybe. It's about a function, the graph of a function stretched. Okay, so that's exactly what it is. If you have x squared and then you have 2x squared, what happens? The graph stretch horizontal vertical. Okay. So this is interesting. If we are, as we did, represent functions by coloring them. Okay, so once again, blue negative, red is positive. You can see what these transformations do to it. It's literally, you can see a shift, intact string of numbers, colored string of numbers is shift. Okay, so these are the first two. The third one is flipped. Also, you can clearly see it. Okay, and then you can see what the stretching and shrinking. What does it do? Question. What you see what it has done? The x is the original and the y is the transformed it. What has happened? So compare this. This is what I'm looking at. This part. So you see the difference in coloring. Ignore the numbers. Numbers are known. What has happened to the color? Lighter, yes, but more importantly,
Softer compression.
right, the contrast. Contrast is what has happened. So the contrast was 1 and then it had decreased. At the bottom, it actually increased when we shrink. You can try a balloon, and draw something on it, and then you blow it, it will become lighter, but really it's gone. Okay, thank you, Class dismissed. See you.